All right, if I can have everybody's attention, we're going to get started. So welcome to the Dam Safety Training Series. I'm Pat Gamble with CDM Smith. We've got quite an interesting presentation set up for today. It's actually in two parts. So the first part is going to be presented by Steve Whiteside. Just a little housekeeping first, though. There is a sign-up sheet going around. So if you want a PDH for the attendance, please indicate that. Sign up on the sign-up sheet and indicate that for me, and we'll send you one. Let's see, what else was there? Okay, so we're going to do this in two parts. So the first part is going to be a 45-minute session. We'll take a 15-minute break, and then the second part will also be 45 minutes. So for the first part, we have Mr. Steve Whiteside presenting. Steve is a vice president with CDM Smith out of our Raleigh office, and he leads the dam and levee practice. He says he has 42 years of experience, but we haven't verified that. I believe him, obviously, but Steve has a BS in civil engineering from Duke University, and MS and engineering degrees in geotechnical engineering from Stanford. And what Steve did not put on here is that he's also a Columbia native, Columbia, South Carolina. So let's welcome Steve.
Great. Thanks, Pat. Can y'all hear me okay back there? Good. All right. So like Pat says, we're going to do this in two parts. I'm going to talk about basically spillway systems, and then Tommy's going to talk about some details for the pipes, around pipes, pipe cradles, anti-seepage collars, and filter diaphragms, and filter design in general for dams. Now, you can kind of read that, but we tried. This presentation is going to be on the SharePoint site when we're finished, so you can have all these references. There are all kinds of references here from the Corps of Engineers, ASCSO, NRCS, FEMA. They all deal with spillways and pipes and filters. So all these are very good references. Look, y'all all seen this. This is from the FEMA's Pocket Guide. It just points out what we're going to talk about. Two kinds of spillways. This is kind of a chute spillway. Then you have a typical riser barrel type spillway, and some issues along that pipe where piping can occur. We have a dam right now, as we all know, up in the North State, is having an issue with piping along the pipe. Again, just another picture of the riser barrel system. Okay, so I'm going to go over several kinds of spillways. Now, this is not a complete list, but these are the ones you may typically see in South Carolina. You have the riser barrel, the siphon, the concrete OG, and other ones I'll talk about. So we'll go through each one of these. Now this is it came from the Bureau of Reclamation. It's a summary of pretty much all spillway types. The ones we'll talk about would be part of these. It's divided into two parts. These are controlled spillways where you may have gates, fuse gates, a siphon. You have to have human involvement to control the spillway. And the ones on the right are all uncontrolled. You know, like a chute spillway, riser barrel, all those just rely upon whatever happens to it. It controls the water. This is a typical NRCS riser that you see on a lot of the watershed dams. We have the drop inlet, and then you have a gate in there for a low-level outlet for the dam. And this one here has a kind of interesting kind of water supply intake. A lot of times they may have an intake like this, or may have a separate tower for just a water supply. But this is a typical NRCS spillway type. This is one. Actually, this is Came to Bureau again. This is more out west. They have some of these morning glory type of drop inlets. You see, it actually has a curved inlet, and it looks like this. It looks really nice. You're worried about the vortex, which means if it doesn't go in smoothly all around, it kind of gets more turbulent at the edge. It's loss of efficiency. So you try to avoid having the vortex effect. That's what this has a lip here to kind of cut down on vortex forming. And here, another one again. We're going to talk about the whole system here, the intake. This has anti-vortex piers out here. So it exits in a chute. They have a stilling basin. So we're going to talk about stilling basins also today. Another figure about the riser barrel. It shows different parts here. Notice this has anti-seepage collar. It's spelled wrong too, but we couldn't fix that. But Tommy's going to talk about this in detail. Basically, in the old days, the dam designers used anti-seep collars, but now they've had a lot of problems. Actually, in some cases, could cause failures by putting these in. So now the standard of care is a filter diaphragm or seepage. You try to control seepage. You can never stop seepage. So you have to control it, make sure it doesn't cause any damage. And finally, here's another kind of stilling basin we'll talk about. Okay. In terms of your standard riser barrels, this is a weir equation over here, where you have a weir coefficient times the weir length times the head. That's basically the flow that can get into your structure. And that's kind of the universal equation. And the different spillways have different weir coefficients. In this case is about 3.1. So you do your hydraulic analysis, figure out what kind of flow you need to pass to keep the water down to a certain elevation, and then you size your spillway based on that. And these are showing two things. This is a circular one on this side with an anti-vortex wall. We don't see that a whole lot on the ones we inspected, but this is a typical kind of concrete box intake. Now, in terms of the philosophy in designing a spillway, this is a schematic, but the flow coming into a spillway and going out can be controlled by different parts of the system. The first one shows the crest control. Basically, that's when this allows so much water to come in and go out. The second one has it's called orifice control. Basically, this orifice right here is really limiting the capacity. So it's the pipe is, in this case, is oversized. It's not flowing full. So you're kind of really not using the full capacity of the pipe. So the best is you try not to have orifice control, but have it full pipe flow, so that you're taking advantage of the capacity of the pipe. There's some pictures. These are some of the NRCS risers we saw in the recent inspections last year. This area actually has two of them for two different levels. This may have been an emergency spillway and a primary spillway. And this is kind of a typical layout of an NRCS riser. The key thing here, you see, here's where inlet is actually up here, so it's inside the cover. And this is to really keep debris out of this, and actually reduce the chance of clogging up this riser here. And the key thing is, see, this is D in width and 3D in length, kind of front to back. So that's kind of the typical dimensions for it. Some intake some barrels. Here's a debris guard up here on these CMPs, a concrete box, a very small riser over here for a small lake. It's one of our dam inspectors on the job right here. These inlets, a big part of the system is the trash guard. You know, there are different kind of trash guards. These here, right now they're very clean, but over time it's going to. We've seen a lot of clogged up trash guards. They need maintenance to get material off of it. So there's other styles which these still look all clogged, but we see a lot of these less chance to clog. Some material, if you have debris on here, it may fall off when the water drops down. But this is the best one up here. So basically, it's a 55-gallon drum on top of a riser. I guess that may work. Actually, this one does have like a vortex bar across there. Okay, so that was riser barrels. We see that a lot. Those are typically the primary spillway of choice in most dams. We talk about siphons. We had a talk a few months ago about siphons, so I won't go in detail about siphons, but they're good we've seen them both for rehabilitation for new spillways, or some dams actually had these in the original design. The way it works, you have a siphon here. This pipe here actually keeps the normal water level in the reservoir. Better picture here. That's the basically the siphon works as long as the water is above the bottom of this pipe. It's going to be siphoned out from the lake. Once it drops down below there, the suction breaks, so it stops until it comes back up again. So it's basically, you need to set this level where you want the normal pool. Okay. Another type you see a lot, that is the OG spillway. That's the shape here. You see these with concrete dams, also with embankment dams. It's a large discharge capacity for a shape. One thing I want to point out, Pat was mentioning, it's efficient because down here, the water in the drop inlet, the water drops right down. It's very turbulent. Then it goes out. This it goes over to the shape's calculated, so it's just a smooth transition out, so it gets more of efficient flow down the spillway. Here's just examples in South Carolina. Some of these are not really true OGs. This looks like closer to a true one than this is more of a OG at the top and kind of straight down to the bottom. But like I say, they're very efficient. This one here actually has flash boards along the top, it looks like, to increase the capacity increase the storage capacity of the lake. This is a project we're working on up in Massachusetts. See, it needs the inside the dam is pretty good. The outside is having some issues. But it has an OG spillway built into the center of the concrete dam. Like I say, here's a weird equation again, and the for an OG, instead of being a 3.1, it's about a 3.7. So you see, it's a little bit more efficient for the length of the spillway. And this is for uncontrolled free flow. You can calculate what this flow is going to look like. If you had, okay, here, this is a shape. It has a certain equation that was developed for an OG. So when we do a design project, we've done some new OG weirs, and typically on the drawings would actually, one has this equation. The contractor might not figure that out, so we put actually have coordinates along every so often along the shape of it, so you can make its forms that way. Some dams have an OG, but also have like a radial gate up here, which it could sit here to raise the water level in the dam. Here, okay, here's a full surface. You raise the gate, then you got water coming out. In this case, it's actually an orifice control, kind of like that previous one with the drop inlet. And so there's a different equation for that. That's the orifice equation. So if you have this kind of system, you can figure out what it'd be a different discharge amount. Okay, so that's, well, feel free to ask me any question as I go through. This is next time is a labyrinth spillway. Basically, you see these both in new dams and existing dams. A lot of dams either got upgraded or design floods got changed, and now you need more spillway capacity. But there's no place to go to get you can't make a longer spillway. There's not enough room in the dam or in the abutment. So actually, a labyrinth allows you to get a longer weir length within the same width of the spillway. Here's one. Yeah, each one of these is called a cycle. You can tell that the total length of the weir is much longer. It's usually like 3 or 4 times the width of the spillway itself. So you get a lot more capacity. Just no one looking down on it. But a similar one it's called a piano key. You see the picture on the right. This looks kind of like a labyrinth. In different cases, this is more efficient than a labyrinth and vice versa. But it's the same idea to really get more spillway capacity within a certain width of a spillway. Let's show this comparison here. This paper down here, is it in the list, Tommy, this paper? It is, okay. This compares, there's a test that were done to compare piano keys with labyrinths. It's a good paper, so it did a lot of model tests. We found that when the piano keys has better capacity in certain cases, and the labyrinth has greater capacity in other cases. You see here here's a cross section through the labyrinth. It's basically just a wall right here, where the piano key there has it's sloped on both sides like this. That's part of the design, makes it efficient. The next one is just a straight chute. You see these lie for either primary spillways or auxiliary spillways, either in the abutment or sometimes over the dam. Like I said, sometimes it's a principal spillway, and sometimes it could be the auxiliary. This is the North Saluda Dam. It's up in Greenville County. It has a chute spillway over here in the abutment. It was a close-up. There was some seepage that we observed in the spillway. You can kind of see it in this case. This is at the discharge at the end now. Here's big concern with a chute spillway is that, especially if you have a very steep spillway, like North Saluda is very steep, so is Table Rock, the same owner to the two dams, and you could have build up, if water gets under the spillway, you have high pressure, especially as it travels under there. At the end, if you have a slab right here, like an 8-inch slab, you'd only need like 1.6 feet of pressure underneath there to lift it up. And that's where it's actually safety of 1. Any more pressure, you would start to crack it or cause an issue. And so a lot of these have drains, under drains, under here. Sometimes there's actually a continuous crushed stone or that kind of material. This one actually has pipes every so often, a graded filter around it that discharge out. And you have these keyways here, or spaced down in a slope. You have a steep spillway to kind of give more sliding resistance. If you need any more than that, you can actually have anchors coming down in there. So between all these pieces here, you could try to design that, try to reduce the chance for uplift pressure, but also provide, tie downs or ways to mitigate any kind of other forces. And a good example of this, you probably all recognize the Oroville Dam. It's been in the news for the last 2 years now, but it had that very problem with the whole thing started with the slab uplifting, and once the one piece went up, you got water underneath, started scouring out, and pretty soon you had this whole area the slab was gone. And there's several reasons. There's a really good forensic report out there that was published, I think last month or month before. I really recommend that. They looked into all the factors, and some of the main factors were it had an underdrain system, but first of all, the slab was very thin. You got the spillway was like 1,000-some feet long and very steep, and had like a 12-inch thick slab. And with the underdrain, they didn't. That last slide had the underdrain down here, but they actually put the drain up into the slab. So now you only have 7 inches of cover, and that's going to crack at some point in time. And then the other thing they had was they had anchors spaced. I think it was, I forget the spacing, but it says into sound rock. Okay, but it turns out that the sound rock was really not that sound. There was a disconnect between the original designers and what the people saw in the field. So it's important for your assumptions that you do during design to make sure when you go to the field, make sure they're still applicable and make changes if you have to. So they found, when they went back and looked at it, the rock was very bad. They looked at some of the records from the investigation. It was not sound, so they should have something differently. So all these different factors went into it. So actually, they've already got it back and running, pretty much like a temporary repair. It was the whole repairs. I think it's going to cost like $200 or $300 million to fix it. Because they have to fix the chute spillway plus the emergency spillways over here, I think. And it was damaged also. It almost failed. Here's some chutes, other chutes in South Carolina. Yeah, a step chute. Actually, you see a lot in roller compacted concrete dams. There are several in the state. They're basically stepped. You have steps come down, maybe 1 foot or 2 foot deep, high steps. What that does, it actually helps to dissipate the energy, and so then you don't have to have quite as long of a stilling basin. With an RCC dam, you can build a spillway in the middle of the dam, which is very, very cost efficient, especially if you have a narrow valley, if you can fit this in. So that was a quick look at several kinds. We're looking at what kind of spillway to actually use. These are the factors you look at. Basically, is it a principal, auxiliary, or emergency spillway? That's the first thing. And then is the foundation rock or soil? Is it good rock or not good rock? How much room you have for the spillway? Whether or not you want to have gates or no gates? And how much capacity you need? Of course, that's kind of the key part to it. And then at the end, how you can convey the flow away. And this is for the Bureau. These two slides. This has all the different kinds of spillways over here, controlled, uncontrolled, with those factors across the top. So you would go through your project and figure out, okay, which one makes more sense for the project. And that's just the second page. So this is a very good summary. Again, this is in the presentation on SharePoint. Okay, so now we've got the water in the spillway. Now it gets to the end. We can't, we want to try to avoid a lot of erosion damage at the end of the spillway. So you have a lot of times some kind of stilling basin at the end. I won't do fluid dynamics, but basically it's a fluid number. is the number you calculate. Basically, the water is going to come down, steep spillway, and at some point it's going to have a hydraulic jump. When the velocity is very high, it comes down, it slows up, then it takes a jump. So you want to try to calculate what that jump is. If the true number is basically if it's less than 1, it's called subcritical flow. Equal to 1 is critical flow. That's like right, it's kind of steady. Then you got supercritical flow, greater than 1. This is an equation that tells depths in the jump before and after the jump. So it'll look like this. So here's some figures showing the jumps. This is a pre-jump, very low energy. This is like, here is a, it says range of good jumps. I guess these are good jumps. These are true numbers between 4.5 to 9. Then you got more turbulent down here. So basically, it's still in basin. You want to try to keep that jump, if you can, within the basin. Otherwise, it's going to. Here's one. This is the first dam we inspected last year. We got there. This was a homemade energy dissipation system. It was like grouted riprap here with some bollards. It was like a bowling alley down at the bottom. It appeared to be working okay, but it was really a homemade. So that's one kind of still basin you could have. Other ones have a little bit more sophisticated, chute blocks and insills in there to help slow down the water. Got some. Here's a good shot here. This is a chute blocks back here. It's called a dentated insill at the end of this. This one here has a splitter wall to kind of for 2 different conduits. This is some other photos of woods in South Carolina out there. Another one, this one, different shapes. This one actually has these 2 pipes share the same still basin in this case. So here's so different. The Bureau of Reclamation has different types. Types 1 through 8, I think, or at least 6. The type 1 basin kind of relies upon just making it long enough so that the jump stays within the basin. Type 2 actually has these chute blocks and a dentated sill. So basically, you're trying to make it so it's subcritical flow out here. So it drops off the energy. So by the time it leaves here, you've got the flow kind of control, laminar flow going out. There's a type 3, which has a chute blocks, the insill, plus you have the baffles here in the middle. So it basically depends upon what kind of flow depths. So one of these may be more efficient than the other on a given project. And here again, here's the profile of the water going out. This type 6 basin is also called an impact stilling basin. These are very good for pipes, especially when you have not much property left. You have to really want to reduce the velocity very quickly. So you have this very compact system. And the way it works, here's a cross section. The water comes out, hits this baffle here. It has to come around, go out, and it has riprap on the downstream side. So by the time it gets out to here, it should be, most of the energy has been dissipated. We saw a lot of these around the state. They're called different shapes. And they're used for pipes, and also if you have culverts coming out, you can use it for that too. You see, it really, most of the energy is gone right here at the end of the basin. A couple more photographs, one's in action. Another type of basin, the plunge pool, you see a lot of these, especially on the NRCS dams. The NRCS has criteria how to design a plunge pool, depending upon the flow. And These can work really well. This is from FEMA. Talks about how you design this basically the size of the stilling basin for a given flow depth, flow discharge, also for the diameter of the pipe. You think basically if smaller the pipe, this is the flow per size of the pipe basically, and you can have a large flow coming out. It's not quite as over a big pipe will be not quite as destructive as a really high energy flow coming out on a smaller pipe. Here's this photograph somebody saw. Not sure who this is. It looks fairly safe, but this is a very large plunge pool. It looks like it's in pretty good shape. The riprap looks like it's held together very well. You know, a lot of these have, especially NRCS, have the toe drain pipes coming out right next to the outlet pipes. And also you see it has a pipe, this has a pipe cradle underneath it to support the pipe coming out. Okay, so that's still basic. Now, when we briefly talk about gates, we don't have a lot on, there are all kinds of gates you can have for either for letting water out, have it on the spillway crest. You have, like I said before, low-level outlet would be at the bottom of this tower, and probably that tower also to be able to drain the lake. There's one that's kind of off to the side from a inlet. So it basically needs to inspect it at some point, make sure this works. They should operate these routinely. A lot of the dams we went out to, they haven't operated those for quite a while. That's what they don't want to do during the inspection, because you might get it open, you might not close again, or it might shear off when you try to turn the rod. So we try to not avoid that, but they need to do a controlled operation. They should do it regularly, like once a year. This is one type of gate on the crest. Before I showed you the radial gates before, which are basically you can rotate on a trunnion up and down. This is a crest gate. It's used to increase capacity. So here's the water level under a full pool. If you need to have lower the lake down, you would drop this crest gate down. And the water, so you could drop the reservoir, increase the capacity of the spillway. So some examples of gates we saw. Can't really tell what these were, but these are gates that could be raised up and down with a hoist. And these basically it looks like they have stop logs. There are some gate mechanisms back here behind there. That's it. That was about 40 minutes. Close. Any questions? Yeah, right. Definitely. I remember last year, I remember we all sat around and had the same discussion. And first, we were going to tell, yeah, the governor, someone said, what, get in lower the lakes. But, mhm. It's a good question. Right. Oh, yeah. Right. And in our cities, you actually get on top, a nice flat surface to work from, too. That's what some. I guess if you look through the, probably is, if you look at your flow uh, rates and volume and go through different calculations. And also look at how much space you have and what the ramifications of if you did have erosion out there. A lot of factors goes in. Yeah. But you can, you really got to look at try to optimize that still base for bigger dams especially. That could be a lot of money, and it has the same problems with spillway too. You have uplift pressure. So you got to think about that. But we had a project. We actually had a big dam. We did a big spillway. Then we were able to use the steps on the compacted concrete to get that velocity down enough to kind of shorten it up some. So you got to look at that also, how the spillway ties into that. You make sure the riprap's big enough. Yeah. I mean, if you calculate what size riprap you think you need, make it at least 25 to 50% bigger and thicker. It might work. Right. Next.
I have one fun thing before we break. So, you know, what's this? He likes to get away on the hydraulic secret. The water resources engineer, you know, what we do is very detailed and not very sometimes. So if you get away half of my secret, then what's the weirdest place? So I like to say that 8% of my work can be done with two equations. The weird equation and the whatever I say. It's your place. Let's be back at 1 o'clock for second one. Oh, no, you don't. That would be a very self-serving job to establish a position for a boat inspector or a riser inspector and then select yourself for that position. That'd be great.
Dangerous, hazardous job.
Very hazardous. Nobody wants to do that. You'd be out there with a camouflage fishing pole while you're doing your inspection. Just sampling, you know.
They wouldn't see me for weeks at a time.
Time for a check-in from John.
That's
Where
right.
is he today? We'd have you on the collector so we could
That's
get
right.
all
I'd be
that.
on the front. Not a bad idea. I bet John Litton, we can talk if he wants to do something in retirement. He might be willing to do that for us.
I asked him if he was coming back to volunteer.
Yeah.
He was surprisingly silent.
I told him if he wanted to keep working, we'd find stuff for him to do. Even like, even from home.
Yeah.
He wants to be done.
Does he? He's got big plans.
Yes.
Yeah, so I wrote down, kind of interesting, I was trying to follow your timeline a little bit. I was writing down where you were. You were right on track the whole way through. Yeah, you were right on track. I think that's a perfect level of focus. Showing up to keep the emphasis if they want to know how you can calculate. It's much better to not have her go to sleep. Would go up 1 full feet. That's the new time. That's the year. Yeah, yeah, question. Visible, take the auxiliary spillway, do some pipe, put them to the wrong portion in the middle.
I don't think you should turn it off. He said as long as this is on, they have the recording.
Yeah,
Or marathon on the TV studio.
that's right.
sand filter? When I go over the loss. So I have to ask him to calculate how much going to be the loss to make sure the riprap will be sustainable. Because I talked to him yesterday, and he said, well, I'm pretty comfortable with all these requirements, because that's and I said, what are you doing now? I just thought about it. It's kind of confusing situation for me. Like, so if you order stuff like that, and I said, well, this is just talking about that we discussed the other day with that guy, we were logging
Uh-huh.
with the spillway in the middle.
Yeah. Yeah. Mm-hmm. Usually you do want to go up to the next standard size, because you're never going to get a D50 or 13 inches or whatever. You need to go to the next standard size. Yeah, I've seen it in the federal references. They give it in both ways depending on what you're doing. 2 would be the max, and 1.5 is the min. But you still need to observe 1 time T max as well. So 1 time T max. Yeah, those are good. We've actually seen a move away from grouted riprap to what they call partially grouted. So the theory is that if you grout everything in place, it forms a rigid structure. If you partially grout it, you make bigger conglomerations of a small expansion. And those can still articulate without having that, often fully grouted riprap undermines, like you found out. So partially grouted riprap can still move, but it forms a bigger unit, so that it cannot be flow. That's the new technology. Federal highways is using partially grouted now. Yeah, totally porous. If I could have your attention, we'll start with the second part. Did everybody get a chance to sign in? If you didn't, the sign-up sheet is up here on the clipboard. There's two sheets. Yeah, as long as you stay through both. Okay, so for the second part, anti-seep collars, cradles, and filter diaphragms, which I know you're anxious to hear about. Tommy Evans is going to present. Tommy has been with CDM Smith, Tommy, about 3 years, and has about 10 years experience as a geotechnical engineer, working mostly on transportation, earth and embankment and retaining wall projects. Tommy is licensed in North Carolina and South Carolina as a graduate of NC State University. So let's welcome Tommy.
Thanks, Pat. Okay, it is my pleasure to talk to you, as you know, about anti-seep collars a little bit, pipe cradles, filter diaphragms, and then we'll run through kind of a quick design example of a filter, also a two-stage filter that you typically see, kind of maybe an application around a tow drain. To start off, anti-seep collars traditionally were kind of the go-to for preventing seepage along a pipe conduit. As time's gone on and we've seen issues with this construction method, the industry, I guess, is getting away from using these largely. The theory is that they increase your flow path down your conduit by as much as 10 or 20%. They're typically constructed of metal, concrete, or plastic. Many difficulties are presented during construction, particularly with compaction in and around the collars and the pipe. The design methodology before, say, 1985 was this NRCS TR60 document. It was amended in 1985 for larger dams to basically get away from anti-seep collars. Now, in smaller dams, the 378 there, which is revised in 2002, still has language about proving the adequacy of anti-seep collars. Here's our quote here. That still is, it's a little ambiguous in the guidance for smaller dams. As an industry, like I've mentioned and Steve mentioned, we've moved away from anti-seep collars. Here's some pictures of failures that happened. Some include those directly responsible for the anti-seep collars. Some of these cases were due to dispersive clays, which dispersive clays are a particular material that have an imbalance of their bonds, and when introduced to water, the structure of the clay will just basically, the particles are treated as independent particles, and it's no longer one kind of block. It'll just kind of melt away and disperse. Some of these were thought to be a result of dispersive clays. There's documentation, exhaustive documentation on field practices of determining if you have dispersive clays in your soil. I think they do become a problem in our state, so it's a good check. Some of these other failures are the seepage, the internal erosion that eventually became what you see here, was a result of seepage outside of the collar area. So you can see it didn't actually serve its purpose in preventing that flow of seepage. It rather just found its way through the conduit anyways. During construction, the natural mechanism for soil is what's called soil arching here up against the pipe. And what this does is it creates somewhat of a bridge, like a soil bridge between your excavation and your pipe. and it actually will carry a load and eventually create cracking kind of in this zone, which, as you could understand, cracks open that path for piping and seepage. Another effect of this bridging is it creates this low stress zone. So the difficulty is compacting along the haunch of the pipe, getting this to really set well is a difficulty that you see with really any conduit. Here's really it's a close-up of one of those other pictures, and this is found in the reclamation document, again listed at the start of the presentation. A few issues with this dam in particular were the pipe cradle. Typically, those cradles are designed to extend up to the spring line or the midpoint along the diameter of the pipe. You can see that it's just barely serving as a support on the bottom. The advantage, and I'll get into it here in a second, but the advantage of a pipe cradle is you avoid those difficult areas in the haunch of the pipe that are difficult to compact. This was also a result of improperly designed or implemented collars. Okay, so this brings us to pipe cradles. I mentioned before the big benefit for the pipe cradle is that you don't have to, or I guess you can avoid those compaction issues in the haunch areas of the pipe. It'll also distribute your load. So for having a larger pipe conduit, you know these pipes get very heavy, and if you're traversing soils that are sensitive or soft or whatever the case, they tend to distribute that load a little bit better. Here, notice the sides of the excavation are vertical. This is more of what you see in practice here. The slant here on the edge of the cradle has a unique advantage of when the soil around it settles up next to the cradle, it actually makes that firm contact. Whereas you can imagine the soil out here, which is more responsive to loading, will settle and actually tend to move away from the cradle. Here's one of our typical details from a project that Steve's familiar with, but you'll notice that the sides are kind of offset towards the center of the pipe. The pipe the cradle will extend up to the spring line. The cradle themselves are reinforced and should be designed accordingly. Here's a kind of a schematic of the conduit through the dam. It's a little bit hard to tell here, but the pipe cradle extends all the way from the drop inlet, or I guess in this case it's a gate structure, all the way down the conduit and actually into the filter, which we'll talk more about filters in a few minutes. Like I mentioned, they're usually for larger diameter pipe conduits. I don't think that they're necessary in all cases, but I think you do avoid a lot of problems that you'd see during construction. Now here's a kind of a, I wouldn't say typical construction. There's a few issues that kind of we've pointed out as we've developed this presentation. Some of those issues are the join here, is it called the bevel? The bell spigot, that's right. So this creates a discontinuity along the pipe. Any discontinuity creates basically added probability that you'll have problems down the line with the way that water kind of moves. Steve mentioned, and I thought it was important, that you're never going to stop seepage. You can only slow it down. These kind of discontinuities speed it up and make it more likely to happen. A few more issues here are you notice I mentioned the slanting towards the pipe. When they go and they cast this in the field, the edge of the cradle is actually away from the pipe. So that soil will settle underneath the cradle, and there will be small voids enough for seepage to basically be encouraged. Yes, and actually, I didn't include another picture, but what they do is they I'm not sure about this one, but typically you'd set your rebar under your supports here, and then you'd pour kind of a high slump concrete and around the pipe to form it in place. That's a good question. I don't remember seeing reinforcement. Okay, yeah. So this is the job that Steve was a part of. Notice the pipe. It's a PCCP pipe. The tongue and groove connection here, and then they actually grouted over the connection, which is standard, to kind of get rid of that continuity. Pre-stressed concrete cylinder pipe for those in the back. Right. Here's another picture of that same job site. You can see here the grouted continuities. There's a picture here of the cradle. This is a well done cradle. You can actually see the slanting and the extending up to or beyond the spring line here. Okay, now we come to filter diaphragms and Did I answer your question? Okay. Filter diaphragms. Here's a general cross-section through the dam. You can see the chimney here, often referred to as a diaphragm, and then the blanket kind of along the conduit here. The diaphragm itself has some typical dimensions, and I'll get into it a little bit later. And this shows a 2-foot thickness here. NRCS has a 3-foot minimum for high hazard dams or larger dams. So this may be more of a small embankment dam schematic. I guess I'll also mention the 3x3D is consistent here as well. You've got 3 diameters to the side, to either side of the pipe, and then 3D above the pipe as well. Again, this 3D on the side with a pipe cradle included here. The filter material is typically a sand material. ASTM C33 would be an example that's commonly used in the area. The construction practice, and I've seen this done a few times in the field, you could do kind of one of 2 ways. The first way, you would actually lay your core or your shell wherever you were along the dam. You would compact it and do what you needed to do to get it up to spec. Then you would excavate and place your fill. You would then compact by using vibrated lifts, or in addition to water, you generally want to have slightly wetter than normal, just to make sure that you don't have those void spaces when you're installing the sand. And then you'd repeat the process. So you'd lay that second lift of fill. And if you can imagine, this is really kind of coming up the backside of the dam usually. These can be installed as a rehabilitation of a dam. So you would come along the back slope and do this kind of and move in sequence in lifts designated by the engineer up the backside of the dam. Our other installation method would be to actually form the filter berm and then lay soil and compact it on the side as kind of the whole layer, and then repeat the process. This is a little bit more descriptive process of the installation. Here you see kind of along the center line, the conduit of the dam. The pipe is, I guess, being laid out beforehand. They go and they install the filter and they vibrate and they wet the sand, and then they move up to where they're basically in line here with the pipe and will continue above the pipe. Now, the way that filters work is it's ingenious and it's so simple, but this internal erosion, as said, will happen at some point along your dam. And the way that the filters work is that the soil eventually erodes on the sides of this flow path here and is caught in the void space of your filter. And this will continue to happen until the hole is basically stabilized and no more material is able to move into the filter. On the other side, you shouldn't be seeing soil. On the daylight side of your filter, you should not be seeing any soil, but rather the clean water. Clean's a relative term, but here's some more pictures of this is actually them setting the keyway in the dam. They came back and they installed a specific clay as the core, and then installed the filter on the back side of the dam here. I should have gotten better pictures. Often you're in the field and you take pictures and you think they're very descriptive, and you bring them back and it's not quite what you thought. But this is on the back side of the dam, kind of looking into the dam. Guidance exists also for the depth below your cradle, and that depends on your settlement ratio. So the sides of your trench will settle at a different rate in magnitude than the beneath the pipe. Obviously, the weight will be different, and so that will dictate how deep you need to go based on the pipe diameter. For example, the settlement ratio equal to 0.7 or more, then 2 feet is required beneath the cradle. When you encounter rock within 1 foot of your excavation, it's better to go ahead and excavate down to rock rather than leaving your filter here and there being this beautiful flow path right beneath. I think you'll lose the benefit of the filter altogether. So this is in a case where you have rock down here. Okay, so this is for a flexible pipe. So you may avoid the cradle being a flexible, maybe smaller diameter pipe. This is just showing kind of the different conditions that the design criteria allows. Notice here that you're actually going 2 pipe diameters on every side for your diaphragm, rather than the 3. And then here's, as I mentioned, for high hazard embankments and large dams, I guess significant 2 high hazard embankments, so our 2s and our 3s would require a minimum thickness of 3 feet. Smaller dams may have a 2 foot. One thing to note here is the few times that I've seen these done, the contractor may have a problem with this 3 because his bucket size is 4 feet. We don't have any problems with increasing the size. It's more material, but it's a lot I guess, easier on the contractor to get in there with one bucket than have to either order a smaller bucket or do anything by hand. So generally, 4 feet will pretty much cover any scenario. The location of the filter is typically on the downstream side of the dam. There are applications where you'd have a filter on the upstream with variable reservoir levels, maybe with levee design to kind of prevent flow of your dam soil to really either side of the dam. But typically what we'll see is the cutoff trench and the filter diaphragm will actually begin at this point. Downstream of the center line, you typically will have a minimum of a 2-foot cover of your soil so that you don't have migration of your filter. You start losing your filter outside of the dam that it's not going to be beneficial to you. And then also, I guess the permeability of the filter should be, I guess, greater than the core, and then something comparable maybe to the shell material. I think that's generally what this figure here is showing you. Okay, so as far as the filter design goes, here's just another kind of an overview of the filters. Here's your main 2 criteria. And again, this comes from the soil conservation manual, these tables. The first thing that you need to do is determine your base soil category. Maybe I'm missing a slide, but the design will vary based on your base soil, and that's typically your dam soil embankment. The soil categories are 1, 2, 3, and 4, and that's based on your fine content or that material that goes through a gradation test and passes the 200 sieve. So if there's a greater proportion of that material that makes it past that 200 sieve, that will be, I guess if it's over 85% of your sample by weight, that will be a base soil 1 category. Most soils exist in this state, kind of between the 2, 3, and 4 range. Down at the coast, you'll get those high plasticity clays. So that's kind of what you see, kind of the 85 range. And then based on your base soil, the soil that you're filtering against, you have different criteria here. The terminology or symbology here in the design is, just to remember, is the lowercase d is your soil in your dam, and then your uppercase D is your filter. So first things first, you get a soil sample of your dam. Typically, you'd want to get a sample pretty close to where your filter will be. As you well know, soil varies from inch to foot, so trying to get a good representation of what your dam soil will actually be. You run a gradation test here to get your breakdown of material passing each sieve. And essentially what that test is they get the soil and they dry it and run it through a series of sieves that vary in opening size, larger at the top and smaller at the bottom. And you get this gradation table here. So the first thing you do is you determine that you're passing 200 here, which is 0.075 millimeter sized openings. The sieve names, for those of you that don't know, that number 200 represents 200 openings in 1 inch. So those are very small holes. And then, of course, the number 4 would be 4 openings in 1 inch. So you're looking at something in the almost 5 millimeter range. So you have your passing 200, and you determine wisely that it's a base soil 2 category, because we have something between 4 and 85% passing the 200. Known broadly as sands, silts, clays, and silty clays. Then what you'll do is you'll plot up your commonly available materials. These all come from the ASTM. Locally, we have, as a transportation engineer, I use the 2007 standard specifications for highway design. There's known filter gradation. So in order to be a ASTM C33, you'll have a range of percent passing at each sieve increment. So you'll plot these ranges here, and what you'll see is, it's orange on my screen. That looks like a brown. This is our sand, and then as you move to the left on the larger grain size on the x-axis, you get into like a 57 stone would be this yellow here. And so when you go and you sample at the quarry or the stockpile, the idea is that gradation for that material would fall somewhere within this range. So going through the design, one of our first hurdles is that our D15, again, more on the nomenclature here, the filter for the diameter at which 15% is passing should be less than 0.7 millimeters. So we come out and plot this on this log chart. Now it's on a log chart so you can see it all together. If it wasn't, it would be spread out and you wouldn't quite get the benefit. You also want to make sure that it's should be not less than 7 and also greater than 0.14 is what we come out to do in following the design charts that were shown several slides ago. So you can see that our ASTM C33, let me go back, is the only one that kind of falls within that range. So I've eliminated these other two. They're just going to be too coarse up against our base soil that we took a sample against. Next, we're checking for gap-graded materials. And this happens sometimes when you blend two different materials of different gradations. Sometimes you'll have material, the gradation tests will show kind of several hoops or maybe like a vertical line, and this test here generally gets rid of those gap-graded materials. And what you have with gap-graded materials is that the filter itself will be unstable. There'll be larger voids where if it's a consistent material, you'd have basically smaller voids. The test is that your maximum at your D60, so that would be here, over your minimum at your D60, that ratio is less than 5. We'd also check for segregation, which sometimes happens if you're at the borrow pit and it's a big pile of soil, and generally the material at the top will fall down and eventually segregate itself based on grain size. So at the borrow pit, typically they go and they cut back there at the toe and try to get you a sample for your filter on the inside of the stockpile. But this check here is that your D10's got to be less than the 20 millimeters if our filter meets this criteria. So we meet that design check. So for this base soil, this ASTM C33 would pass all of those criteria. Next, we look at what may happen if you need two different materials. Essentially, this would happen around, like a common example would be tow drains, where you'd actually have two different gradations right next to each other. So the way that you would design that filter is then treat this first filter, in our case the ASTM C33 sand, right next to, I guess, the coarser material. And here's a kind of a detail of a tow drain. So you've got your sand here, and this isn't our scenario. We didn't use the 78M in our example, but I guess this illustrates that gradations vary from region to region. But we do have this 33 sand next to a gravel, which is next to a pipe. So we'll also look at the size of the openings of the pipe as well. I mentioned the black book, or the standard specs for highway design. These are common gradations, and you'd use these, like I said, these ranges to plot these up on your sieve chart. And this is how you get the ultimately you get those shapes that you use for design. This is the coarse aggregate, and from right to left you actually get, this is fine, and this would be coarser. I think everybody is familiar with the 57 stone here, and then this is a finer side over here. And then these are even finer aggregates. Okay, so we're treating our C33 as our base soil, and the main criteria here, and actually I'm going to go back a few slides so you can see it. Here we go. So our base soil category in this case is our C33, which is actually going to be the sand and gravel, because we have less than 15% passing. So our criteria here would be different from what we used before. We'd actually go down here and see that 4 times our base soil category, our filter, should be greater than the filter's D15. So just remember that chart. Okay, so we use this criteria. Here we find that our D85 for our filter, our base soil in this case is our 33 sand. To be conservative, we choose the smallest size, i.e. the smallest opening, or the smallest grain size range at the 85% passing. And we see that, that this 57 stone is outside of this range here. So our 4 times 1.1 is 4.4, and here we can see that the yellow, the 57 stone, is too coarse for the 33. So we chose the 789, which is a finer, it's a finer material than the 57. Or 789 is actually over here, so you see that more material is passing these finer sieve openings. And we see that it does meet that criteria, so that same 4.4 is here, and this falls within this range. So lastly, we'll look at the actual openings in the pipe. What we want to avoid is the 789 stone getting into and clogging the toe drains. So the check here is that the D85 would be greater than the diameter of your pipe hole. So we see that the D85 is 8 millimeters, which is roughly 0.31 inches. Sorry, my units aren't here. But this is greater than our hole size of say, 1/4 inch. So we would specify a 1/4 inch. Now, if our design plans may have 1/2 inch openings, we'd see that this would mean there's too much of the material that's getting into those holes. And the D85 is used for, I guess, based on experience. So that completes our design example. So, does anybody have any questions? Ooh, I don't have a feel for that. You said 103 NRCS stems? Yeah, so I'd say most of those, actually probably all of those, would have cradles in some capacity. Well, hopefully you'd never see it. Well, I'd say, at least with the NRCS dams, that a lot of those probably have some kind of filter. I don't know if they'd have maybe the state-of-the-art filter diaphragm that's described here, but generally when you have, especially when you have those toe drains, Steve showed a picture of several pipe cradles at a plunge pool, and you have those toe drains extending out along with the cradle. Those are typically from some kind of filter. So I would think if you've got toe drains, especially those that are working, you've got a filter.
Maybe a better way to go about that. That guy that you were showing, cradle and all that, what,
85, right.
85, that was kind of when it started. How many residential built after 85? Basically, what we're saying is we got a whole bunch of dams that probably don't have any cradles, that don't have any diaphragm.
Yeah, I'd say that's a pretty fair assumption. And Steve mentioned the chimney here. So the idea is to capture this phreatic surface within the chimney. And if this is designed correctly, the seepage is controlled by the chimney and the blanket here. And then collected into the toe drain and exited the dam in a controlled fashion. Okay. Mm-hmm. Yeah, so the flexible versus that rigid pipe. So this would be like your HDPE pipe, your plastic pipes that basically would have some movement associated with them. I don't think this is necessarily recommended for many of our kind of medium to high dams. But this is within the criteria. So yeah, good question. Yeah, what does he win, Pat? Right. Right, and I think this schematic probably is, yeah, yeah. Cradle's a good practice to go. It kind of, you're avoiding those problematic issues that are, it's just really difficult to overcome. Getting that good compaction by hand or smaller tools is difficult to do. We're starting to. Right. Yeah, and it is a difficult construction procedure. It's not overly complicated, but I think your average. Right. So particularly here, I would say this would be a good example of where the workmanship really should be kind of cared for carefully. You've compacted soil over your filter. Now, what they don't really show is that this excavation needs to happen in such a way that the filter is basically daylighting in the bottom of your excavation. You don't want to have like even a thin layer of soil right here. Well, you've just destroyed the functionality. Right. Right. So a little bit more care is required, and yeah, it doesn't make it to your toe drain, for example. Yeah. Any more questions? Yeah, I can go back to that slide. I threw a lot in there on this one. So this is your cross section. I guess the main criteria, if there was one, would be that it's downstream um, of the center line here. It's going to be on the downstream side of your cutoff trench for any of those zoned embankments where this is kind of like what you see here, where the core material is a less permeable material than the shell is. That diaphragm that is placed on the back side of your core. Does that help you any, Scott? Okay. Yeah, you work with the engineer.
I have a few more giveaway goodies for you, but I don't have any more questions. So if anybody needs a bag, come on up. Thank you.